In the previous lectures, we explained how we could create loops using the assembly instructions and jump. In this lecture, we are going to introduce you a couple of other instructions which are somehow are useful for implementing if and else in higher programming languages. If you have worked with other programming and higher programming languages like C or Python or Java, you see that the most important commands and instructions are if, else, and also loop. Almost all of them have been implemented using jump instruction in the assembly. Jump would look at some specific flags in the rflags register, as we explained in the previous lecture. These flags are like zero flags, carry flags, and other kind of flags, and we control these flags by other instructions. Comp, CMP, or compare is one of these instructions, or subtraction or addition or decrementing or incrementing are other kind of instructions which would change these flags. So we would just use these instructions to change the flags in the rflags registers, and then the jump would jump to a specific location based on the result or based on the flags of these instructions, or the changing and the updating of these flags in the rflags registers. The instructions that we are going to talk about in this lecture are addition, subtraction, comparing, and a couple of other instructions. So in here I just want to create the file. I say nano, let's name it just compare dot nasm and hit enter. Actually, let me just copy one of the files that we created before. So I copy it into a new file called compare.nasm and hit enter. Now we enter the compare.nasm, and I want to just cut all of these lines except the exit system call in here. So first of all, I want to move a value like 5 into the R10 register. I also want to move, let's say, the value of 2 into the R9 register in here. And now I want to use the compare R10 and R9. Compare is exactly like subtraction, which we've worked before. If I use the subtraction in here, is equivalent to the compare. The only difference is that the registers wouldn't change. What it means is that the changing of the flags in the because of the compare would be the same with the subtraction. The only difference, as I said, you just imagine that compare and subtraction are exactly equal. It's just the compare result wouldn't change. None of these registers would be changed because of the compare. So in here, instead of me just changing other values and showing it to you, I just want to first disassemble it and go one by one in our file in here. So what we expect is that 5 gets subtracted by 2, which would be 3, but the result wouldn't be saved in the R10 register. Instead, we want to just check the if flag. So in here, I just save this. I go in here and disassemble it. Now we execute the compare, hit enter. It has been executed successfully and exited, but we want to enter the file using the GDB in here. And first let me break it at the start and we run it. I also want to dump the using the obj dump. I want to disassemble it also. So obj dump in here with the Intel format and hit enter. These are all the instructions. Now I run in here. If you look right now, the RIP register is pointing to 4080, which means that we are at here to move the value 5 into the RD register, R10 register. If I just say info registers and RIP, you could see that 4080 we have. Also, if I see the values, the content of the R10 register, you would get 0 because it hasn't been executed yet. So I say step I, this has been executed. Now the RIP points to 4086 and the value in R10 has been updated to 5 as you see in here, which means that the first instruction has been executed. But the main purpose of this lecture was to look at the E flags or R flags register. If you look right now, the 0 flag is not set in here. What I'm going to do is to step I through the program and step through it again. Right now the RIP points to 4008C, which is for comparing R10 and R9. If you look, the R flags register still doesn't have the 0 flag or carry flag set. We step I and hit enter. Again we look at it and it still isn't set in here. Now this PF is the parity flag and is set when the result of the last operation, the number of set bits in the result of the last operation are even. What I mean is that, for example, in here the last operation was to subtract 2 from 5, which would be, well, compare is subtraction, right? 5 minus 2 would be equal to 3. Now the result, the 3 in the binary, would be shown as 0 1 1, right? So we have only 2 set bits or 2 bits of 1 in here, and because we have, well, 2 ones, or it is even, so the parity flag would be set and we have PF in here. Parity flag is also the third bit from the right side. If I go to another shell and enter the Python shell in here, right now the value of the E flags is equal to 206 in the hexadecimal. So I just convert it to the binary and we have 0 1 1 0 0 and so on. The third bit from right is the parity flag, and if you look, it is equal to 1 in here. Now why is it useful to have the parity flag set? Again, it's just for the different jumping that we have. So in here, let us just go to the file again. The jump instruction, which looks at the parity flag or third bit from the right side, is actually just JP. So let's say in here we say jump to a specific location which I want to create in here. Let's not just name it printing. So I just create it so fast, or actually let me just go and in the hello world.nasm, which we created in the previous lecture, and I just copy these 5 lines in here. So this is the file that we are working with, and also I want to copy the lines at the data in here. Copy this, go to the file again, paste it in the data section, and what you are going to say is that JP and then the printing label. So what this JP does is that it would jump to the address of the printing in here, which would be here, only if the parity flag or PF is set. Right now it is set because the result of 5 and 2 would be equal to 3, which has an even number of 1 bits or set bits in itself. So if it is not set, then it would move and exit. Right now, let's see if we have done it correctly. So I just save it, exit, and disassemble it and link it and execute it, and as you see, we have hello world printed on the screen. A lot of times we have actually a loop created. The reason for the loop is that first we are at the start, right? So we move the number 5 to R10 register, then we move number 2 to R9 register, then we compare it, which would result in setting the PF flag or the parity flag. Then the jump would look at that flag and it sees that it is set, so it would print at this section. The right system call would happen. You would have hello world on the screen. Then we get to the start in here. Again, 5 would be moved to R10, 2 would be moved, compare would happen, and JP again would see the PF set and would happen to printing again, and this would happen again and again. So just using the compare and JP, we were able to implement a loop.